Hello everyone, I'm Ramadan and in this video we're going to see how I've implemented a 4-bit boot multiplier high level synthesis using C language using vivado. So the first point to be noted is that as it's a 4-bit boot multiplier, we can use the numbers from 0 to 7 and it can be either signed or unsigned. So it can be like positive sign or negative sign or not signed at all. But we can multiply numbers only between 0 to 7 as 3 bits will be assigned for the actual numbers and 1 bit for the sign. So here we have the three main steps you have to follow. The first step will be use any code editor to create the code. So we are creating the code in C. So first let's see the booth algorithm. So for 4-bit booth multiplier, we're gonna create and we are going to like repeat the steps for 4 times. So the first step will be depends on the q1 plus 1 and q1. So if it's 0 0 or 1 1, we directly shift 0 1, add and shift 1 0, subtract and shift. This is what happens for 4 times in the loop, and this how I implemented in C. So there's a booth multiplier top level function, and we are taking two inputs, multiplier and multiplier, initializing two variables q naught and accumulator as 0, then some it's like 2's complement, sorry, negative numbers 2's complement, then negative for changing the multiplicand to 2's complement for using it for the like subtraction in that this part. So this part we are subtracting it, right? For that I'm using this neg 1, and with 0 0 or 1 1 directly shifting. This is what we can do for shifting. This for 0 1 means we have to first add then shift. Got it? Next, if it's 1 0, we have to first subtract. I'm adding with neg because it's the 2's complement of the multiplicand, and shift. This is how I have implemented the code. And next is the result. If it's negative, we have to change it to the 2's complement form, or we can just directly we can just directly return it. So this is returning a variable. So I have a header function also for declaring the function for the for like for C's understanding, and for both test.c is the test bench for the C file. And we have given like two variables. We can check this thing. So if we give the correct answer, we're gonna get the command, and if it's like a wrong answer, we'll get error. So we can check with this, and we can even multiply signed numbers with this. So it should be minus 10, right? Yes, we are getting minus 10. So with this we can test it. So this we are going to use it in the Vitis HLS. So let's go to Vitis HLS. So here you can see this is Vitis HLS. So here I've already imported the codes here. So this is boot.c and this is boot test.c. So here I've already run the C synthesis, which will be transported to the RTL, and I've exported it to RTL. So as I've already done it, I can see the summary, synthesis summary. So here I have the old, thing, and yeah, this is what my synthesis summary was. So I got some pretty neat stats over here, some input output information, and some pipelining loops and stuff. So that's what I've got, and we can also function call graph. So function call graph, one loop, two loop, three loop, four loop, and till seven loops. And there is another thing we can see. There's a report over here. So this report is, we have already seen this, and we can also see the schedule viewer. This is how this schedule is viewed. So these are some stats which we do not need to bother about right now, but I have already synthesized it and exported it to its vivado IP. So vivado IP is with which we have to work in vivado. So I have already exported its IP. So with that IP have already designed the booth multiplier, added a design. Here we can add any IP we have in our system. So we have that booth multiplier IP over here. I've already created it, and that's going to be in a zip file. So this zip file we can put it in the same directory as a vivado project file, or else we can directly access from anywhere. So as we have this booth multiplier, I've imported it. So it has like few ports over here. Let me show you. So this is a booth multiplier. It's like there's some. Okay. These are the ports of it. AP start is an input. AP done, idle, ready are some outputs which we don't need to bother about right now except the done one. And we have a clock over here. So this clock is being given by a simulation clock generator. And we also have a app reset which is also generated using this sync reset over here coming with the clock. So this is what we are going to give for the clock and reset. For the multiplicand, we can give a constant, two constants. So with that we can verify using the simulation. So I've given here -3 and -4 here. So the output should be technically it should be 12. So that's what we're gonna see with the like after the simulation. So here's the whole thing. So we have a done over here and a written over here. So written will be the answer or the product of the two numbers constants. So we have to get a 12 right. So I'm going to run the simulation. It's already saved. So I'm going to run the behavioral simulation. So it's going to take some time. It's only the first time that takes this much time. So we can see it's just thing. We can run it for 10 milliseconds. As you can see, we get 000C, which is wrong, right? This is because we didn't connect, convert into its radix. So if we convert it into its signed decimal form, we get 12, which is the answer. Like -3 into -4 is 12, right? So this is the answer we get here. So we can check it with another value. We'll open the block design and we'll change this to the other one is -4, right? Wait a second. The other one is -4. Sorry. Yeah. The other one is -4. So here we can change it to 5. So if it's 5 into -4, it's -20. So that has to be our answer. So I'm going to save it here and I'm going to run the simulation. I'm going to run behavior simulation and it's okay. We can have to discard it and we have to create the simulation. So it's running the behavioral function and we're gonna get the wave. Okay, we are going to run the waveform for some seconds and we'll get FFFFEC, which is wrong, right? It's also because of the radix. So if we convert into a signed decimal, we get -20. 5 into -4 is -20, as we expected. So this design is running. So this is a design we got away. So this design is running. So which means our booth multiplier is synthesized. We can then synthesize this using this, and we can export into an application project, and we can continue it further. But the scope of my project stops over here. So that's it for today's video. Thank you.